So, good evening, doctor. I would start off with my demonstration of my robotic arm joint. So basically my robotic arm joint has four parts, one being the PVC pipe, one being the lower part of the joint, and one being the upper part of the joint, and one being a pin. So I would start off with the explanation of the PVC pipe, which is a very simple design. It's basically just an outer diameter of 20 millimeters with an inner diameter of 16, and when we measure, we would get a wall thickness of 2 millimeters, which is the same as the specification given. So, and then after I draw it, I basically just boss extruded 150 millimeters. This got changed. I just extruded 150 millimeters upwards, and I got the PVC pipe. So there's the PVC pipe, and we would go on with explaining the lower part of the design. So basically my design have a female part and a male part, and which the male part would clip to the female part, and then they would be secured by a pin through the central extrusion hole right here. Through this hole right here, it would be secure. So we would start off with the male part, which is the upper part. So this is actually the design that use most of my time. Actually, they have the same time in terms of file properties because I save both file in the assembly, and I use an hour and a half to design both of this. So I would start off with by explaining with the um the male part of the design. So this is for fitting the PVC pipe up here, a a circle, and then this is the physical angle limiter, the physical angle limiter. So this is the male part, which is actually just a sector. We will go into the sketch. It is just a sector of 90 degrees, and they are 45 degrees from the center line to the, I would call this the positive part, and I would call the other side the negative part. So they are 45-degree to both of the parts, and they would be tilted when they are in the assembly so that they would face the z-axis, and then they could rotate up from the z-axis or rotate down from the z-axis. So rotating up would be positive and rotating down would be negative in this case. Basically, I just draw two lines, and then I just define the angle to be 90, and I make these two dots to have a uh, horizontal relationship, so as to having them have the same angle from the middle line. So that is basically the male part, and then I have just extruded that part of the section out 1 millimeters so that it could clip onto the female part when they are being assembled. So that's basically it, and my assigned angle is 24 degree to the positive part and negative 34 to the negative part. So I achieved that from my lower part of the design, which is this extrusion right here. This is an extruded cut into the surface. So I would go into the sketch and we can see. So since I need to go 24 angle towards the positive part, then by means of the middle point we have to move 24 degree, and also the other surface would have to move 24 degree. So that is basically just 45 plus 24. That's how I got the angle 69, and I have declared the positive maximum angle to be 69, which allows the sector on the male part to move 24 towards the positive side. So that's how I got the number, and similarly I got the number 79 by taking the sum of 34 and 45. So that's how I got the maximum angle and the minimum angle. And then after I designed this, I basically just extruded cut into the surface 1 millimeters, and I just linear pattern to the other surface. So basically how they would be assembled is basically when you have the male part and the female part, they would go together and clip together. Then you could insert the pin to secure them together in place. I can show the pin. The pin is basically the same thing, but the pin is basically just a cylinder of the same radius and length of 23 millimeters. If we look at the extrusion, it's just 23 millimeters, which is slightly bigger than the width of the both of the design. So we go on with the I won't rebuild. I would go on with the design, the final assembly design. So this is basically the joint. I have make it. Okay, let me untransparent it. Okay, so this is the final design. This is the PVC pipe, and this is the joint. So let's first measure the dimension of the whole joint to ensure that we are not exceeding the 50, 50, and 50 dimension. I would hide the PVC pipe, and we can measure the dimension in piece. So first off, measure the delta x, which is the x dimension, the length. Let's go to the front plane, and then we can measure. So this is at its initial state, which is after assemble, it would be like this. It has not been rotated at all. So if we go back to the front place, we can see that its width is basically right here. Its length is basically right here to right here. So that is 23 millimeters in delta x. So it has a 23 length. And then we now need to measure its height, which is the delta y, which is from here to here. Oops, not this face, the edge. The edge. Okay, so it basically has a height of delta y of 22 millimeters. So it is not exceeding the limit. And we need to measure, next up, we need to measure the width. So let's go to here. So we can see that the width is basically from this edge to this edge. So that is 28 point something millimeters, but basically it's 28 millimeters because I think I selected the inner edge. I should select the outer edge. Okay, so yeah, it is 28 millimeters in distance. So it has a 23 millimeters length, 22 millimeter height, and a 28 millimeter width. So it is within the dimension of 50, 50, and 50. So next up, we would show that we would show the rotational motion first at the maximum and minimum. Okay, so I would first explain how I angle mate both of the thing by making it transparent so we can view it better. I would first explain how I mated it. So if we go back to this part, we would be doing all the rotational motion from the left. So you can see that it can rotate upwards and rotate downwards. So how I angle mate it is basically I have angle mated the upper surface of the male part and the female part, this face and this face, to have an, oops, this should be 0. I don't know why it changed. Okay, so it basically have a maximum angle of 58 and a minimum angle of 0. A minimum angle of 0 meaning that it is both of the surface there is touching, which means it is at the minimum angle, and the the joint needs to move 24 and go back to the z-axis and need to move negative 34 to the maximum angle. So in total, when we take 24 plus 34, we get 58. So that's how I got the maximum mate angle right there. So that's that. I have 58. And now I would demonstrate the rotation. I mean the max. Okay, I would demonstrate the rotation. So in order for us to know that the angle mate is actually working is if we don't so I would like to re-record this part of the video because I did some mistake during the first time recording. I would demonstrate how my physical angle limiter actually work in action. So this is when when we have the angle mate. So of course when we have the angle mate, we would see that it is functioning as usual. So it would start at 24 and it would end at negative 34, which sum up to an angle of 58. So we have a minimum angle between these two faces of 0 angle minimum and 58 angle maximum. So that is how I achieve this with the angle mate. But even without the angle mate, even when I suppress the angle mate, let's go back and then let me suppress the angle mate, and then even without the angle mate, even when I rotate it, the angle should directly stop at here, which would be negative 34, and it will also stop at here, which is 24. So if I take collision detection and stop and collision, when I rotate, you can see it would exactly stop at this angle, and we can check this. If we measure this two angle, we can check this by measuring this face with this face, and we should get the angle 58. Select others, and let me select this face. We should get the angle 58. So you can see we get the angle 58. That means that it is at its maximum. That's when this pipe is at negative 34 degrees. So that's how we check the physical angle limiter is actually working. And here I actually have a tolerance of, let me check. I think it's 0.1 millimeters. The tolerance is, yes, it is 0.1 millimeters. And the tolerance is used to ensure that when we 3D print, because the circle wouldn't be a perfect circle, so putting some tolerance can smooth the rotation, and that is basically it for the demonstration. This file is because I have changed some of the configuration, so it takes like um 10 hours, but because I just changed something before I recorded the video. So the design is basically from the lower part, which is it takes almost 1.5 hours, and the upper part, which is also 1.5 hours in total. So I would say that's the most complicated design, and the PVC pipe is just a simple design that took me 2 minutes, and the pin is, I think, approximately also, yeah, just 2 minutes, slightly off 3 minutes. And that is basically all from my presentation, and